So, in the last few lectures we have been looking at correlations for momentum transfer. Momentum transfer in the flow through conduits, we had looked at pipe flow if you recall, where we had distinguished between two regimes, a laminar and a turbulent regime, and what has to be predicted here, the dependent dimensionless group, is the friction factor, which is a scaled wall shear stress, and it is also a measure of the pressure difference across the pipe required in order to drive the flow. That is a function of the Reynolds number based upon the average velocity and the pipe diameter and the fluid density and viscosity. And just from dimensional analysis, the friction factor is a function of Reynolds number. It is different depending upon the flow regime, whether we are in a laminar flow or a turbulent flow. Laminar flow with straight smooth streamlines and no cross stream velocity fluctuations, the flow profile is parabolic. Turbulent flow with turbulent eddies mixing across the cross section of the pipe, the velocity profile is more plug like at the center and sharper at the walls, and there are fluctuations in all three directions in a turbulent flow, even though on average the velocity profile is the velocity is only along the axis on average. And the friction factor is 16 by Re for low Reynolds number, and it varies at high Reynolds number depending upon the wall roughness, and I had discussed a correlation for the pipe flow. Flow past a flat plate with negligible projected area perpendicular to the flow. The drag force on this flat plate is primarily due to the shear stress exerted on the wall. Once again, the flow regime depends upon the length in this case. If the Reynolds number based upon the downstream position is less than about 5 into 10 power 5, the flow is laminar. Beyond that it becomes turbulent. The stress exerted by the plate on the fluid causes a disturbance to the velocity of a fluid within a boundary layer of thickness delta close to the surface. That is because momentum is diffusing from the surface and it is getting convected downstream. Therefore, the effect of the plate is felt only within a boundary layer close to the surface, and we had looked at the scalings for that boundary layer. It goes as the boundary layer divided by the downstream location scales as Re power minus half in a laminar flow and minus 1/5 in a turbulent flow. And we had also looked at correlations for the skin friction coefficient. The drag force per unit area tangential to the flow per unit area of the surface divided by half rho times the free stream velocity square. Okay. We had looked at flow around a particle, the different flow regimes, all the way from the laminar flow with symmetric streamlines between the downstream and the upstream hemispheres, down inertial effects for Reynolds number greater than 1.5 less than 24 causes an asymmetry, and then there is a separation bubble at the rear. This separation bubble, when the Reynolds number increases above about 400, you get vortices being shed periodically in a wake region. Above about 4000, this you do not have this periodic shedding, it becomes a turbulent flow in the wake. And when the Reynolds number exceeds 2 into 10 power 5, the wake is turbulent, the attachment points of the wake shift downstream, and you have turbulent flow in the boundary layer upstream as well. And we had looked at the drag coefficient as a function of Reynolds number. Less than about 1.5, Stokes drag law holds is valid, and CD is 24 by Re. Above 1.5 till about 400, you have a correlation which incorporates the effect of inertia at low Reynolds number. Okay. Above about 4000 or so, the drag coefficient is a constant about 0.4, and at 2 into 10 power 5 you get a drag crisis. The correlation for the bubble does not contain all these complications because the flow profile does not contain all these complications. Provided you are in a clean liquid with a clean interface, no surfactants etc., there is no boundary layer separation and so on. the flow can be well approximated by a potential flow, there is no turbulence. At low Reynolds number, the drag coefficient is 16 by Re, and at high Reynolds number it is 48 by Re. And we had looked at the definitions for a packed column as well. One has to be careful here in how to define the equivalent diameter and the velocity through the voids. Okay, you have to look at the void equivalent diameter and the void velocity, and those are related to the particle equivalent diameter and the void fraction. Particle equivalent diameter and void fraction are ultimately the parameters that are used, okay, for defining the Reynolds number and the friction factor, and these are the definitions. And we had also discussed the Ergun correlation for the friction factor versus Reynolds number in this case. Okay. So, now we will look at mixing. Okay. An essential component of many unit operations. Okay. Typically, in a reactor you have an impeller that is rotating, okay, and mixing the fluid, and the kinds of the design criterion here is likely to be for a given volume of fluid and for a given impeller geometry, shape, etc. What is the power that is going to be required to mix this fluid? Okay, so that is the question, or what is the torque, okay, required for this. Okay. So, a complicated geometry is a priori difficult to solve. Okay. So, what is usually done is to make a scale model. Okay. In which all the geometrical dimensions are kept a constant, that is the ratio of the impeller width to the tank diameter, the length to height, the cross section to the height of the tank, the level of fluid, etc., is all kept a constant between these two. Okay. And in this scale model, which is maybe 10 times less or 100 times less, you would like to measure what is the power required in this model, and then relate it to the power required in the actual system. Okay. So, when you do this, there are one thing is of course the ratio of all length dimensions have to be kept a constant for similarity, okay, between these two. Okay. However, the also to be kept constant are the relevant dimensionless groups. Okay. Also to be kept constant are the relevant dimensionless groups. Okay. So, rather than expressing this in terms of the total power required, you would like to express it in terms of the power number. Okay. The dependent dimensional variable is the power required, okay, the power required in order to drive this impeller. Okay. And this power has dimensions of mass, okay, length square, energy is mL square T power minus 2, power is energy per unit time, okay, energy required per unit time. So, this mL square T power minus 3. Okay. Recall that force is mass into acceleration mL T power minus 2, energy is force into distance, okay, so mL square T power minus 2, and the power is mL square T power minus 3. Okay. And this can depend upon various independent dimensional parameters. Okay. It could, for example, depend upon the frequency of rotation Fr, which has dimensions of time inverse. That is the number of rotations per unit time, for example, per minute or per hour and so on, and the diameter d with unit of length. Okay. And of course, it depends upon the fluid properties, the density rho with m L power minus 3, and the viscosity mu with dimensions m, L inverse, T inverse. Okay. So, now the power number has to be defined based upon these parameters. Okay. There is one dependent and 4 independent parameters, and therefore, there are one dependent and one independent dimensionless group. Okay. So, there is one independent and one dependent dimensionless group. Okay. For scaling the power. Okay. In an actual reactor, there will be other parameters also that enter, and we will discuss that a little later. Okay. So, you can scale this either by the viscosity or by the density. Okay. You can scale the power either by the viscosity or the density. The power number is defined as P scaled by the inertial scales, okay, by the fluid density, okay, rho the frequency cubed and d power 5. Okay. So, this is the definition of the power number. It is scaled by the inertial scales. Okay. You can see that in the denominator it has dimensions of mass length square t power minus 3, which is identical to what we had over here. Okay. You can also get this by simply by dimensional analysis by substituting p times rho power a, f r power b and so on, and you will get exactly the same thing. Okay. So, this is power by inertial scales. You could also scale it by viscous scales. So, you would scale it by inertial scales when the Reynolds number is large. Okay. So, what is the Reynolds number in this case? Okay. The Reynolds number Re is equal to rho times f r d square by mu. Okay. F r is a frequency. Okay. F r times d square is equivalent to a frequency times the diameter is the characteristic velocity. Okay. So, this is equal to rho characteristic velocity d by mu, where this characteristic velocity is equal to the diameter times the frequency of rotation. Okay. So, that is the way that you get this Reynolds number. Okay. And when Reynolds number is large, you would scale it by this. When Reynolds number is small, you have to scale it by the viscous scales, of course. Okay. And you can get that quite easily by just dividing this by the Reynolds number, dividing the power by the number by the Reynolds number. If you divide the power number by the Reynolds number, the density will cancel out, okay, and you will get it in terms of the viscosity. I am sorry, if you multiply it by the Reynolds number, the density will cancel out and you will get it by the scaled by the viscosity. Okay. So, power number times Reynolds number is equal to P by mu f r into d cubed. Okay, that is the power number scaled, the power scaled by the viscous scales. Okay. So, how do we use this in scale up? Okay, as I said, we have to keep all the dimensionless groups a constant. Okay. So, let us take an example. Okay. A reactor, okay, with of diameter meter. Okay. Designed to rotate with frequency 1 second inverse, okay, 1 rotation per second. Okay. Mixing liquid of density 1 kg per meter cubed, I am sorry, 10 power 3 kg per meter cubed, and viscosity I am sorry, 1 kg per meter per second, let me change that. And liquid air this is the surface tension. Okay. So, that is the requirement to design this a reactor with this impeller of diameter 1 meter designed to rotate with frequency 1 second inverse, mixing liquid of density 10 power 3 kg per meter square and a highly viscous liquid 1 kg per meter per second. Okay. And the liquid surface air surface tension is 0.1 kg per second square. Okay. A model reactor with, okay, this is a scaled down reactor, a model reactor with diameter 10 centimeter. Okay. Is designed to estimate power required in actual reactor. What is the rotation rate and liquid density and viscosity to be used in model reactor? Okay, so that is the question. Okay, what is the liquid density and viscosity to be used in the model reactor? How does power for model reactor compare with actual reactor? So, those are the questions. Okay. So, I have a large scale reactor with a fluid and it is rotating with 1 second inverse, diameter is 1 meter, and I design a smaller reactor, okay, 10 centimeter, right, and it has to rotate with some frequency for the model reactor. Okay. It has to rotate with some frequency for the model reactor. Okay. How do I relate the frequency, the liquid properties for the model reactor with that for the actual reactor? Okay. So, for that now we have to make sure that one, the dimensions, the relative dimensions of the reactor, the impeller, etc., are exactly the same for both cases. Okay. The ratios of the dimensions. we also have to ensure that the relevant dimensionless groups are the same for both of those cases. What are the dimensionless groups here? Okay. So, one of them is of course the ratio of density and viscosity, okay, the ratio of inertial and viscous effects, the Reynolds number. Okay. So, dependent group is the power number, which is equal to rho rho f r cubed d power 5, that is the dependent dimensionless groups. The independent dimensionless groups are the Reynolds number, rho f r d square by mu. Okay. Now, as this impeller rotates, that interface is also going to deform, okay, because of centrifugal forces. Okay. So, let me just rewrite this. I am sorry. Okay. And then there is the Reynolds number, which will be rho f r d square by mu. Okay. Now, the interface is going to deform because of a balance between gravitational, centrifugal and surface tension forces. Okay. So, there has to be a gravitational force balance as well in this case, because we have to make sure that the relative deformation of the interface is the same in order to get the accurate prediction of the power, okay, between the model and the actual reactor. Okay. So, the Froude number, which is okay, f r square d by gravitational acceleration. Okay. Froude number is f r square times d by gravitational acceleration, that is the ratio of inertial and gravitational effects, or centrifugal and gravitational effects, that determines the shape of the interface. The other thing that could determine the shape of the interface is the Weber number, okay, which is the ratio of inertial and surface tension forces. Okay. Rho d square, I am sorry, d cubed f r square by surface tension gamma. And we can compare all of these in order to estimate which are the dominant effects. Okay. So, let us look at what is required for the real reactor. Okay. The power number we do not yet know, okay. We have to estimate that. Okay. The Reynolds number, rho f r d square by mu, density is 10 power 3, okay, kg per meter cubed, frequency of rotation is 1, diameter is 1 meter, viscosity is 1 kg per meter per second. Okay. So, therefore, this Reynolds number is equal to 10 power 3, okay, for the real reactor. Okay. The Froude number, I should correct my mistake here, this is equal to square root of that, okay, it is equal to square root of f r square d by g. Yeah, okay, this is a square root of that. This is equal to diameter is 1, f r is 1, gravitational acceleration is 10 meters per second square. So, therefore, I have root of 1 over 10 is equal to 0.316. What about the Weber number? Okay, the Weber number is rho d cubed f r square by gamma. Density is 10 power 3 meters kilogram per meter cubed. D is 1 meter and f r square is 1. The surface tension in this case is 10 power minus 1. Okay. The surface tension in this case is 10 power minus 1. Okay. Therefore, this is equal to 10 power 4. Okay. So, clearly inertial effects are much larger than surface tension effects. So, I can neglect surface tension altogether. Gravitational and inertial effects are comparable. So, I have to include the gravitational effects. Reynolds number is large. You might think you can neglect the viscosity altogether, but it is important to note that there could be situations where viscosity plays a role. Okay. So, for example, we saw in the flow past a flat plate that the drag coefficient is proportional to Reynolds number even in the or 1 over the Reynolds number per half, even in the limit of high Reynolds number. That is because the drag force is due to the shear stress exerted on the surface. So, in situations where the shear stress exerted on the surface is dominant, the Reynolds number will be important even in the limit of high Reynolds number. Okay. Therefore, in designing my scale model, I have to make sure that these things are the same. Okay. So, I have to make sure that the Froude number is the same. Okay. So, if I use the notation subscript m for model and I for actual, okay, I require that FRM square d m by g is equal to FRA square dA by g. As the relation between, if the Froude number is the same between the model and the actual, then FRM square, the model reactor frequency square times the model reactor diameter divided by g is equal to FRA square times dA by g. G has to cancel out because that is the same on the earth. Okay. Therefore, I will have FRM by FRA the whole square is equal to dA by dm. Okay. D actual by D model is 10, okay, because the actual is 1 meter and the model is okay. Therefore, FRM is equal to square root of 10, which is about 3.16 times the actual reactor, which is approximately 3.16 second inverse, okay, revolutions per second. So, in order to keep the Froude number a constant, I have to run the reactor at about the model reactor at about 3.16 inverse second, 3.16 rotations per second, which is square root of 10 times that of the actual reactor. How about the Reynolds number? Okay. I require that rho m dm square f m by mu m is equal to rho a dA square f a by mu a. Okay. So, therefore, the density and the viscosity of the model are related as dA square by dm square f a by f m into rho a by mu a. Okay. dA square by dm square, dA by dm is 10, so this is 100 and f m by f a is 3.16. Okay. I am sorry, I should use here f rotation here. Okay. So, I should use the notation f r m f r a. Okay, into rho a by mu a, okay, which if you calculate it is 31.6. Okay. That means that the ratio of the density and the viscosity of this has to be 31.6 times rho a by mu a. Okay. For the system that we have, rho m is 1000, mu m is 1. Is equal to 31.6 rho a by mu a, okay, which implies that rho a by mu a has got to be equal to 31 point, sorry, into 1000 okay. Yeah, okay. So, therefore, if the densities are kept a constant, then the actual oh, I have substituted it wrongly here. Okay, so rho m by mu m, the model is equal to 31.6 into 1000 kg per meter cubed divided by 1 kg per meter per second. Okay. And what that would imply here is that rho m by mu m is equal to, okay, if I keep the density a constant, okay, if I the liquids, you do not have much choice in varying the density. You do have a choice in varying the viscosity significantly, because liquids can go all the way from water with 10 power minus 3 kg per meter per second to very viscous fluids which can have 10 or even 10 power 2 etc. kg per meter per second or Pascal second. Okay. So, if I keep rho m is equal to 1000, kg per meter per second, then the viscosity of the fluid to be used in the model reactor, the viscosity of the fluid to be used in the model reactor to ensure that the Reynolds number is the same, okay, is going to be equal to 1 by 31.6, okay, okay, which will approximately equal to 0.0316 kg per meter per second. Okay. So, if I ensure the Reynolds number is the same and the Froude number is the same, the Weber number is not important between the model and the real actual reactor, then the result is that the power number is the same between the model and the actual reactor. Okay. So, if I use a frequency, okay, if I use this frequency of rotation in the model reactor, this viscosity of fluid in the model reactor, okay, choose the viscosity carefully, okay, so that it has the same value. You can do that by mixing different fluids. Okay. Then the power number P actual by, okay, rho actual d actual power 5 times f r actual cubed is equal to P model by rho model d model power 5 f r model cubed. Okay. So, the actual power is equal to P m into rho model by rho actual, I am sorry, rho actual by rho model into d actual by d model power 5 into f r actual by f r model whole cubed. Okay. I said that the model and the actual viscosities are densities are the same, that means that this is equal to 1. Okay. The ratio of the diameter is 10. So, d by dA by dm power 5 is 10 power 5, and the ratio of the frequency is 1 by 3.16. Note that we had to rotate the model reactor impeller at 3.16 second inverse, corresponding to the same Froude number for the actual reactor at 1 second inverse. Okay. So, this whole cubed, okay, and this is approximately equal to 3162 times the power of the model reactor. Okay. So, this gives you a way of estimating what should be the parameters that we are using in the model system, okay, in such a way that we get the same dimensionless groups for the actual system, and how do we relate the model system to the actual system for the problem of scale up of a reactor. Okay. Okay, so, this gives you an example of how to scale up a reactor, And next class I will also discuss how to scale up a mixer. Okay. So, I will continue that in the next lecture. I will see you then.